Hello, welcome to, this will be our third video in our chapter 18 practice problems. This is quite a long problem here, so we're going to get in. As you can see, I already have some stuff already filled out. Try not to pay any attention to that right now. We're going to start at the very top and work our way down. So number 11 is a researcher is interested in the relationship between BMI and hypertension and has decided to categorize BMI into 4 classes based on national recommendation. The researcher gathered secondary data from various hospitals records and selected 409 cases of hypertension matched to hypertensive-free controls on a variety of demographic characteristics, including age, sex, education, socioeconomic status. The case and controls were then categorized based on their BMI at a weigh-in after signing informed consent. The following table summarizes the relationship between the outcome and exposed variable. So first thing we're looking at is what type of study design is this? And as you saw, I underlined a couple of examples there. And if you have your cases and you're matching them to controls, you can kind of guess where this is going. When you have a disease and then you're matching them to people who are disease-free at the time, this is going to be a case control. Wow, that's horrible. It's going to be a case control study design. The next thing it says, perform a formal statistical test to determine if there's a difference in risk for hypertension between BMI categories. Write out your null and alternative hypothesis and interpret your result in alpha level 0.05. So when we're doing a formal statistic test to determine if there's a difference in risk for hypertension BMI, and we need a null and alternative hypothesis, we're doing our chi-squared test. So our chi-squared test, once again, is shown here. And its chi-squared is equal to the sum of our observed minus our expected squared divided by our expected values. When we do our null hypothesis, which is right underneath it, we're stating that there's no association between the variables. Our alternative hypothesis is there is an association between the variables, and that's all we always state for our chi-squared, is that there is no association and there is an association between the variables. So we have our observed data, so our hypertension, non-hypertension, this is our observed data. Now we have to find our expected data. The way you find expected data is you take your row total times your column total divided by your total, and that will give you your expected value. So this table right here is going to be your expected value table. I've already filled in some of it, the bottom half, so we're going to do the top half though, just to do a reminder. So when we have our 2x2 table and we're trying to find out our value for BMI 1 underneath hypertension, our expected value, so you can take your row total. So if we're looking at hypertensive as our observer, we're trying to figure out our expected value here, take your row total of 87 times by our column total, which is 409, and you divide it by the table total, which is 865 table total. When you do that and multiply and divide, you're going to get a value of 41.1364. So the next one we're going to do is for this expected value of hypertension, non-hypertension. So you're going to take your row total, which is 87, times your column total, which is 456, divided by the table total of 865. When you do that, you're going to get a value of 45.8636. When you do, we're trying to find now the expected value of hypertension in the category 2 row. Take your row total, which is going to be 361, divided by your column total, which is 409, divided by table total of 865. When you do that, you're going to get a value of 170.6925. Same thing when we're doing our hypertension in column 2, row 2. Take your row total times your column total, which we're going to do 361 times 456 divided by 865, and then you get a value there of 190. Sorry, getting a little ahead of myself. 190.3075. And this now is your table of expected values. So now you have your observed and your expected values for chi-squared, and then we're going to put them all out. So right over here now is everything. So you have your 33 as your expected value minus your 33 as your observed value minus 41.1364 is your expected value. So I'm going to put a star next to each one of these so you can see that's what we're comparing, divided by the expected value. And you're going to add it to, change the color up here, we'll do red now. Red, so now you have your observed value of 54, and then your observed value, your expected value shown here, 45. So 54 minus 45.8636 squared divided by the expected value. You do that for every point on the chart here. So we'll make this a triangle just so you can see and match it up. So your observed value to your expected value for every different point. We'll make this a square so you can see that one. And so this one is your circle. The 83 is your triangle. Here's your square value. So you can see where each one of these are matching up on here. I'm not going to do it for all of them. You keep doing that all the way through, and then eventually you'll get your sums. When you get back to your sums, which is here, so if you take 33 minus 41.1364 squared divided by 41.1364, you'll get a value of 1.6093. You add up every value you get here. When you sum them all up, you're going to get a total of 199.81, and this is your chi-squared value. So if you have a chi-squared value of 199.81, that is a high value. You should already kind of know that's a high value. But how do we determine the significance and if we are going to reject null hypothesis or fail to reject null hypothesis? So we have to go to table E. When we go to table E, we're first going to need to know our degrees of freedom, which we're going to take our rows minus 1 times columns minus 1. How many rows do we have here? We have 4 rows minus 1. Columns, 2 columns minus 1. This is going to be 3 times 1 equals 3. So we're going to have 3 degrees of freedom. When you go to table E in the back of your book, you go to the degrees of freedom 3, add an alpha level 0.05, right? Because that's what we're looking at. And you'll see that the critical value there is 7.81. Our chi-square value is greater than that, which means we have found significance at that alpha level. What is our actual p-value? Well, our p-value, if you keep going all the way down, you'll see that at 0.0005, chi-squared to be 17.73. Our value is still higher than that, so our alpha level is going to be less than 0.005. In either situation, we're going to reject the null hypothesis. We're going to reject the null hypothesis, stating that there is an association exists between the variables. Moving on, now we're going to calculate the appropriate risk measure for hypertension based on the exposures of categories 2, 3, and 4, using category 1 as the non-exposure group. Which group has the highest odds? So this one we're using category 1, so we're using category 1 here as our control group. And so that's always going to be your A and B when we're going forward, because that's going to be what we're comparing everything to. So when we compare everything for the next other categories, our odds ratio formula is going to be A times D over B times C. So for category 1 as our control, 2 category 2 group, you're going to take 33 times 278 divided by 54 times 83, which is equal 9174 over 4482, which equals 2.0469. Next one you're going to do is control group 1 to category 3. That one's going to be 33 times 98 all over 151 times 54. It's going to give you 0.3966. And then the last one's going to be group 1 to group 4, which is going to be 33 times 26 all over 142 times 54. It's going to equal 0.1119. last part of the question asks which group has the highest odds. So as you can see here, the highest odds is going to be groups 1 and category 1 and 2 for BMI, with an odds ratio of 2.0469. So based on that, we go down now to part D. We're going to calculate a confidence interval for this group. The way we have our confidence interval, our formula is shown here, where we have e to the natural logarithm of the odds ratio plus or minus our z of 1 minus alpha over 2 times the standard error of the LNOR. Standard error of the LNOR is the square root of 1 over a plus 1 over b plus 1 over c plus 1 over d. So the odds ratio we're looking at here is 2.0469. The way you calculate the LNOR is you go to a calculator, you find the ln button, press ln, then type in 0.20469, and then it'll pop out a number for you, which is the natural logarithm of that odds ratio, and this would be 0.7163. Our z value of 95% confidence is 1.96, and then our standard error for the LNOR is written out like this. When you take the square root of all the fractions here, you're going to get a value of 0.2539. Putting this all together, your formula is going to look like this: 7.7163 plus or minus 1.96 times 0.2539, and this is all member to the e power. So when you multiply 1.96 times 0.239, you're going to get a value of 0.4976. Add that plus or minus to the 0.7163. Remember, always to the e power. You're going to get e to the 0.2187 to 1.2139. Once again, on the calculator, right by where your ln button is, most of the time there's some sort of shift function or a second function, and right above that it'll be e to the x power. You would type e to the x power and you go e to the 0.2187, hit enter, and you'll get your lower confidence limit, which would be 1.2445. And you have to do it again, e to the x power, so e to then the 1.2139. You can't put this all in at one time. These are two separate equations to solve, and then when you do that you get 3.3666, and this is your confidence interval. What does this confidence interval tell us? It tells us that we had an odds ratio between categories 1 and 2 at 2.0469, shown here, and then we found a 95% confidence interval for the group. Confidence interval tells us where the true value lies, so this one's telling us where the true odds ratio lies. So we're saying that we are 95% confident that the true odds ratio for this particular study design, where they're measuring categories of BMI between being hypertensive and non-hypertensive, the true odds ratio for BMI 1 and 2 is between 1.2445 and 3.3666. So that's where the true odds ratio